What if computers didn't deal in absolute certainties? What if, instead of just giving you a straight answer, they worked with probabilities? Well, today we're diving into the strange, powerful world of quantum computing, and we're going to see how it completely rewrites the rules of the game. You know, it all really kicks off with this wild idea from physics. In the quantum world, things aren't concrete. A particle isn't just sitting right here. It actually has a chance of being in a whole bunch of places all at once. It's all about probability. So let's just run with that for a second. What if you built a computer based on that principle? Not on the usual black and white 0 or 1 logic we're used to, but on this whole spectrum of possibilities and chance. And that right there is the big idea behind a quantum computer. It's a machine that's built to actually use the weird, probabilistic rules of the universe to solve problems that we used to think were just impossible. Okay, so you know how a regular computer bit works, right? It's basically a light switch. It's either on or off, 1 or 0. Simple, predictable. But a quantum bit, or qubit, that's a whole different beast. Think of it more like a spinning coin, one that you can actually influence midair. Before it lands, it's not heads or tails, it's a mix of both. It's a probability of being either one. And this changes everything about how you get an answer. Classical computing is a straight line. You set a value, you flip it if you need to, you read the result. Super predictable. The quantum process, though, is a totally different game. You don't start with a fixed answer. You start with a cloud of possibilities. Your job isn't to flip a switch. It's to carefully nudge the odds, to shape the probabilities before you finally take a look, and force the system to pick a side. So all this probability stuff isn't just some quirky alternative. It actually gives quantum computers two incredible abilities. I mean, they're basically superpowers that normal computers just can't touch. First up is something called quantum parallelism. And look, don't confuse this with the parallel processing in your laptop that runs a few tasks at once. No. This is the ability to do a practically limitless number of calculations all at the same time with just one command. Just let that sink in for a second. A regular computer has to work through a problem step by step by step. But because a qubit can be a blend of all its possible states, a quantum computer can act on every single one of those possibilities at the exact same time. Here's a cool way to picture it. A single quantum instruction doesn't just change one thing into another. Instead, it's like it takes all the possibilities, mixes them all up at once, and creates this huge cascade of new outcomes in a single step. All right, but hold on. This brings up a pretty big question. If the system is juggling every possible answer at the same time, how in the world do you get a single, useful answer out of it? It seems like it would just be noise, right? Well, this is where the second superpower comes into play. Before you actually ask for the answer, the whole system is in this state we call superposition. It's not one thing or another. It's more like a cloud of pure potential, where every single possible outcome exists with its own specific probability. You can kind of see what I mean with this chart. Every potential answer you could get, like 000 or 001, has its own little slice of the pie. That slice represents its chance, its probability of being the answer when we finally decide to look. And then you measure it, you take a look, and the very instant you do, that whole cloud of possibilities just vanishes, and it collapses into one single concrete result. The spinning coin finally lands. But this incredible power, it comes with a price, a pretty big one actually, because while we can shape all those probabilities, we can't completely control which answer the system decides to land on. So yeah, the outcome isn't guaranteed. You can run the exact same quantum program twice and get two completely different results. Each outcome just pops up based on the probabilities that you so carefully engineered. So what do? You have to run the whole thing over and over and over again. It's kind of like one of those Gelton boards, where marbles bounce down through a bunch of pegs. You can't predict any single marble's path, but if you drop enough of them, a clear pattern, that beautiful bell curve, starts to emerge from all the chaos. That's exactly what we're doing here. Okay, so you're probably thinking, why on earth would anyone bother with all this uncertainty and repetition? It sounds messy, right? Well, here's the payoff. For certain types of problems, this approach lets us find answers that are practically unreachable for even our most powerful supercomputers. This is the ultimate goal, what everyone in the field is chasing. It's called quantum advantage. See, for some really hard problems, as they get more complex, the power a regular computer needs just explodes. But for a quantum computer, the resources needed can grow much, much slower. And that gap, That's where the magic happens. Let me give you a classic example to make this a little more real: the knapsack problem. Imagine you're packing a bag. It has a weight limit. You've got a bunch of items, and each one has its own weight and its own value. The goal is to figure out the perfect combination of stuff to get the most value without going over the weight limit. Now, with just a few items, you can probably figure that out in your head. But what if you have 41 items? Well, a classical computer would have to check every single combination, one by one. And that's over 2 trillion combinations. A quantum computer, though, it explores them all at the same time, finding that optimal solution way more efficiently. So let's tie this all together. The really big idea is this fundamental shift from certainty to probability. Quantum computers use these crazy superpowers, superposition and parallelism, to check out massive numbers of possibilities all at once. And then, by measuring the results over and over, they can pull out answers to ridiculously complex problems that would otherwise be totally out of reach. And that really leaves us with a final, massive thought. We are just now learning how to build and program machines that thrive on the fundamental uncertainty of the universe itself. So as we get better and better at this, you have to wonder, what other problems that we call impossible today are we going to solve tomorrow?